Good afternoon, everyone. Yeah, so I'm Xishen Xiao. I'm an associate professor at Arizona State University. So unfortunately, due to visa issues, the paper author cannot come. So I will present this paper for the authors. They are my collaborators, but I'm not involved in this project specifically. So I will try my best to present their work, and I can help answer some questions to clarify some concepts. But if you have questions that cannot answer, I can redirect your question to the authors, and I will make sure that they can provide answers to your questions. Okay, great. Yeah. So I think in this work, the project was looking on detecting the OLE vulnerabilities. So first, I would like to briefly introduce what's OLE. Right? OLE stands for Object Linking and Embedding. It's a technology that allows sharing of data and functionality between Windows applications. It was developed by Microsoft in the early 1990s. Right? There are several typical applications of OLE. First is document editing. Right? Usually it's embedded Excel, spreadsheet in a Word documents. Second is presentations. You can actually embedding video diagrams in PowerPoint. Now we're using PDF. If I'm using PowerPoint, it's possible to play a video inside the PowerPoint. The third scenario is data sharing. Usually you can share data between different software applications to maintain data consistencies, such as sharing data between Excel and slides, and PowerPoint. So in this work, first they want to they focus on the OLE 2.0, which is based on the common object model and the structural storage. So the common object model essentially refers to all OLE components, which will expose the interface, allowing the client's applications to discover other interface like IOLE object, IOLE link, and iView object 2 basically is a general interface that you can query in order to understand what's the COM objects that are involved. And then they also provide a structural cover. Basically, the host applications needs to provide the persistence management, and then the applications who use the OLE, they will be able to implement this interface, and then they can store their states. Yeah. So there are two categories for the OLE object that is involved. First is the embedded object, which is a self-contained object that is stored in the host documents, such as Word stored in the Excel. Second is the link objects. This is something that we can easily see that you use a reference to refer to other objects in the certain directory of your computers. So how OLE will work, given this definition, is essentially pretty straightforward. So first, when you have embedded OLE objects, first they are when you try to run the objects, first they are going to retrieve this called like CLS ID from the host documentation, and then they are going to invoke the specific method called the code create instance to load the modules, and then finally they will invoke the load method from the interface, like iPersist storage, to deserialize the OLE object, so then the object can be fully initialized and can be used, such as playing a video. To better understand how these mechanisms may be exploited in this work, the authors they summarize some of the CVE they collected, and then identify 7 types of vulnerability. And here, the major findings have three major findings. First, they found out that for most of the vulnerability, they come from like the embedded OLE object parsing problems, which accounts for like about 43%. And there are also about like 1/4 of the applications they are actually reached the end of their maintenance life, and they are no longer used. And also, there are some of the vulnerability that they are found actually are very difficult to exploit. 13% of them belong to that. So basically, we want to focus on the one that are still valid and can be easily exploited to launch some attack. So after they summarize this attack, they categorize them into 3 types of possible exploits by using the OLE objects. So for the type 1, essentially is intended to loading a COM components that are not intended for OLE. So essentially, as I mentioned, right, to load the COM component, first you need a CLS ID. But turn out that in Windows, you can have CLS ID that are not point to OLE objects. So then it becomes a vulnerability that can be exploited. So essentially, for example, like in one of the CVE 2015-1770, they found out that some of the CLSID will point to the DL OSF.DL, but it was not intended to be a OLE component. So then if you have this, they will crash because when they load this DLL will not be properly initialized and then a crash will happen. For the type 2, it's called the DLL preloading attacks. So this, I think this is similar to other, in Linux command line, right? Essentially, it's like when you have a DLL, they try to look for where the DLL is. And if you do not provide a complete path, usually they are going to search certain folder to see whether that DLL exists in those paths. However, some variation in the Windows installation could lead to path search different folders. So for example, in one of the CVE 2023-35347, when they try to create, invoke the method called create instance in the Windows geolocation services, the get find my device enable method is invoked. In there, they are looking for one DLL called MDM common DLL, right? But that DLL does not exist in the Windows Server version. So if you place a malicious DLL file with the same name, right? Then this application will actually load your malicious DLL, and then you can launch an attack. The third type is the OLE data passing errors in invoking the interface I persist storages. So essentially, the API load is responsible for loading the object stored within the storage sections. Many related vulnerabilities stem from by invoking these APIs. So the problem of this is that you are relying on some kind of checking to see whether the object that you load through this API is the one that you intended to use. But essentially, this is just not properly done, right? So one of the CVE, 2017-1188U, is found in one execution file, and the vulnerability would be lead to a state overflow during the file name passing. Basically, they try to load this, and then they find out that this is actually a fake COM object, and they have some kind of vulnerabilities. So in order, based on these study results, the authors propose a comprehensive approach that consists of 5 phases to automatically detect whether the OLE embedded in your Windows applications has vulnerabilities. So in the phase 1, they first try to automatically analyze the OLE components. So essentially, they try to search the Windows registry to understand the CLSID, and they try to identify the component, and then they analyze the interface. This is very straightforward. By collecting the metadata, you can already resolve the type 1 vulnerability detections. And for the second step, or the second phase, what they do is basically, you want to lower OLE object. One of the problems, some of the OLE object components may require GUI interactions, which usually is difficult to simulate, right? And then the authors identify one way to bypassing this kind of complex GUI interaction is through by creating an RTF for each OLE component, and then they can bypass the user interaction and after that, they will automatically invoke initialization of the component. So in that way, you can automatically initialize the OLE components without compressing UI interactions. And after they initialize the OLE component, what they really want to do is that they try to use fuzzing to see whether they will be able to identify some vulnerabilities or some problems. So basically, for the OLE components, the majority of them belong to ActiveX, right? So what the author do is they manually create some ActiveX components as the seed inputs for the fuzzing, so then they can mutate the ActiveX inputs in order to generate different kinds of mutants that can test the loading function. And for some of the OLE components that are not ActiveX controls, what they do is they try to find out some of the formats that original component contains, and then they are not going to fuzzing as a whole, because if fuzzing as a whole, usually cannot pass in the input validation. So they use a snapshot and then they fuzz chunk by chunk, right? So the detailed algorithm I'm not going to explain in detail, but essentially the key thing is they have an algorithm that can identify different snapshots based on the API, and then they fuzzing different components, and then by combining those fuzzing components, they will be able to construct a new chunk of inputs. So essentially, these are all binary inputs that try to fit into the OLE loading functions. And once you can parsing it, then you have some probability that maybe you can identify some crashes or some vulnerabilities. And after that, once you will be able to load it, and then they can start to doing some behavior analysis to see whether the components may exercise some kind of behavior that are not intended, and then they will be able to perform the vulnerability analysis, right? So this is some of the tools they use, like Windows, you can use process monitors to monitor what kind of API has been called, and what parameter has been passing. And then they can use the Windows debug tool to analyze crash dump and identify whether there is some vulnerability pattern there. So they evaluate their approaches in Windows 10, Windows Server 2019, 22, 23, and Windows 11. They set the default OS setting with the application like Visual Studio and Microsoft Exchange. And they use the desktop to run this experiment. They aim to answer 3 research questions, right? The first one is how effective are the most important components of the approach they provide. And second is that they want to answer how well they can detect the vulnerabilities that's specific to Microsoft Office, and then how precise is in detecting unsafe OLE components. So in their research question 1, they analyze more than 7,000 components on Windows 10 and Windows 11, and they prioritize for Microsoft COM components for their widespread use. Essentially, in the end, they also manually examine 257 OLE objects. And they find out that they identify 4 out of the 3 type 3 bugs in non-active X items, and they also try to experiment without using their micro snapshot fuzzing, try the total one, but that one would be like difficult to find new things. And here is performance results of the fuzzing. Essentially, they found that their micro fuzzings improved early stage coverage via snapshotting, right, instead of fuzzing as a whole. And they also, here is some example numbers, like with the snapshotting on analyze the DL file called ink objects, right? They can do 107 executions, and then without it, you can do more executions. But this shows that even though the speed is lower, but the coverage is higher, so then you have more probabilities to detect vulnerabilities. And in their research question 2, they identified 26 vulnerabilities, and 17 of them have already been confirmed with the previous CVE IDs, right? And also, 18 of the vulnerabilities they found are capable of being exploited for remote code executions. In their research question 3, they identify type 1, type 3 vulnerabilities, and totally they generated 12 crash dump files, and 5 are confirmed as the previous CVE, while the remaining 7 are identified as null pointer that they require further manual representation. Similarly, on Windows Server 2022, they found out the count of the null pointer problems they found is 8. Okay. So that's all I want to talk about. So any questions? Thank you.
Right. I guess even though the speaker cannot answer the question, he can relate.
yeah, I can relate. Yeah. Yeah. Okay. Okay. Thanks,
you. Thanks, speaker.
So hi everyone, I'm Jay from University of Central Florida. It is my pleasure to present our work for today is from large to remote comparative evaluation of large language models in vulnerability detections. So large language models excel at code understanding and generations, making them promising for large-scale vulnerability detections. And however, we still lack of clarity on how factors like model size, context window, and quantization affect the results. So traditional static analysis, static or dynamic analysis relies on external tools. Of course, large language models itself is external tools, but essentially large language models is a tool that can analyze the source code from end to end and give the verdict like a human being. So by evaluating multiple large language model architectures, we highlight each model's strength, weakness, and real-world viability. So these are 5 questions guide our study. First, we measure how accurately large language models detect the vulnerability in file level. Secondly, we see if a bigger context window improves the result. Thirdly, we check whether the quantization hurts the accuracy. Fourth, we compare new model architecture to older ones, for example, Llama 3 compared to Llama 2. Finally, we see if a few label examples can improve the detection accuracy. This is a general pipeline for our work experiment. From left to right, there are dataset preparations, curated datasets, experiment pipeline, and lastly, we do the evaluations. We source our data from two main datasets. One is Vulnerable.j, that's for Java, and Big Vol for C and C++. After retrieving the relevant source code from the GitHub, we use the tree setter to remove the comments and the non-code artifacts, and we then manually filter out some duplicates or incomplete data. Ultimately, we arrive to 280 files for the Java and 200 files for C and C++, evenly split in vulnerable and non-vulnerable codes. We test a wide range of models and to see how various architectures, model, parameter size, and the context window capability influence the detection accuracy. So GPT-4 here is only used as a reference point. So we use a very straightforward prompting tailored for Java as an example here, asking the model for a simple yes or no alongside with a brief explanation. We hold the temperature at 0.5, fix the seed at 42 for consistent outputs, and cap the output size to be 2048 to prevent excessive or endless generations. And this table presents our baseline test where we only input vulnerable code files to each model. We focus on two matrices, AP, that is the fraction of files correctly flagged as vulnerable, and the VAP as the fraction of vulnerabilities each model identified at least once across all files tied to that vulnerability. By isolating the positive samples, we see how reliable these models detect known vulnerabilities under a simpler condition. So this chart is basically another representation for the data we showed in the previous slide. And Java here reaches near at 79% on AP and 93% on VAP. Llama 2 also performs strongly. Models like CoLlama and GPT-4 end up in lower than anticipated, illustrating that specialized or proprietary models aren't guaranteed to excel. So this table measures how consistently the model declares a file is vulnerable or not in a clear instruction following manner. So EP counts the fraction of files that directly says yes or no statement, and the VEP reflects how many vulnerabilities get at least one explicit verdict. So this chart is basically another representation for the table we have in the previous slide. And GPT-4 and the mixture top at 100% here, never missing a clear yes or no. CoLlama and Llama 3 also scores high, showing that newer or domain-tuned models can be very explicit. So in summary, this test on files that are vulnerable, we see no simple rules for performance. Larger models don't always yield higher AP or VAP, and quantization works differently depending on the architecture. Typically, bigger context window help. Overall, the findings underscore a complex interplay of model size, and quantization and architecture. We further expand our experiment beyond that vulnerable-only experiment by adding the non-vulnerable, which is the safe ones for the Java experiment. Since larger context window generally boosts the performance, we use a maximum capacity that is context window for each model in this zero-shot test. The same yes or no prompt applies here. This table is a smaller excerpt from our more extensive result, showing each model family's best performing configuration plus overall top performer on Java. To save time, I'm just directly jumping to the analysis. So from this result, several patterns emerged. First, the certain models emphasize precision, while the others stand out in recall. We also see a bigger parameter counts don't consistently yield better performance. And quantization preference different by family. Finally, advanced or domain-focused variant don't automatically surpass earlier generations. So our C and C++ experiment closely mirror to Java setup with just the code referencing C or C++ in the prompt. So and this experiment still under zero-shot condition using each model's largest context window. So this table is a subset of our larger result from the paper, highlighting a few standout models configurations. And for the analysis that is saying, this experiment shows that the quantization gains depending heavily on model family. So JAMA performs better in FP16, while CoJAMA prefers the Q5KM quantization. Larger architectures often underperform smaller ones, with Llama 3 70B variant even failing to detect any vulnerabilities. So Mistra's newer models like Mistral, that is also lag behind its predecessor. All of this suggests that neither big nor more advanced model means automatically good or better. So in the following experiment, we added 2 label examples, one vulnerable, one non-vulnerable, into the prompt to see if just a few samples that can improve the accuracy or detection rates for the Java. We select the top zero-shot performance, and our goal is to observe whether providing the minimal guidance significantly boosts the accuracy in spotting or detecting vulnerabilities. So this result basically is saying what we are seeing is a consistent drop from the zero-shot to few-shot experiment. The drop in the performance may stem from the expanded prompt overshadowing the actual code or from the example snippets introducing conflict queues. So some models also became too cautious, leading to steep decline in recall. Overall, few-shot didn't boost the detection in this setup. So in our C and C++ few-shot test, each model got 2 label examples as well, but this approach collapsed performance to 0% in precision, recall, and F1. Some models misclassified everything as safe. Others split mistake between false positive and the negatives. So these inconsistent behaviors suggest that minimum few-shot prompts may confuse the model in C and C++. So after testing whether the model can detect vulnerabilities at all, we pushed them to identify which type vulnerability exists. So we only focus on the files that are known to be vulnerable because it is make little sense to classify a type in the non-vulnerable code. The prompt now is asking a CVE ID and a short description. And we measure 2 matrices, AP, and did the model still flag the files as vulnerable? And C, did it name the correct type? We also tried a few-shot setup by providing 2 example vulnerabilities, and though we removed them from the main data sets to avoid leakage. So this table is a smaller slide from our overall Java type identification result, showing each model's zero-shot accuracy alongside its few-shot accuracy. So based on the table, we know that some model maintains moderate AP. Virtually all fails at identifying the specific type. Most remain as 0, or just a few correct case. Moreover, switching to few-shot often lower the overall accuracy. This highlights how multi-class labeling is significantly tougher than simply at detecting if the code is vulnerable. We also examined how context window model size and quantization affect the runtime. So larger context window can slow the prompt analysis phase, but speeding up in response generation phase. Bigger models like Llama 2 and 70B inherently longer. Quantization like Q5KM cuts this time down, striking a balance between performance and the resource demand. So in summarization, so large language models do work for vulnerability detections, but performance varies sharply across language. Java fares better than C or C++, and most models failed to identify exact vulnerability type. And the larger context window help accuracy and reduce hallucinations, whereas the quantization impact depending on each architecture. Surprisingly, advanced model and few-shot learning often underperform. Ultimately, domain-focused tuning and careful prompt design seems vital for reliable real-world results. So in conclusion here, we test 38 large language model configurations on Java and C or C+ vulnerability detection task, seeing that model like JAMA can excel but still greatly by language and setup. Large context window often help, though architecture upgrades like Llama 3 and Phi 3 aren't guaranteed to outperform an old version as Llama 2 and Phi 2. Few-shot prompt can unexpectedly hurt the performance. and the strong Java outcomes don't always transform to C or C++. Crucially, open source containers like Llama or Llama 2 can outperform GPT-4, suggesting practical and cost-effective solution despite these limitations. Moving forward, refining model architectures, balancing the context usage, and improving the prompt strategy should be our focus alongside expanding the broader code domains. And thank you.
All right. Questions? Yeah, it's better to come to the microphone so everyone can see hear your question more clearly.
Hi, thanks for the talk. I'm Tian from University of California, Irvine. So I know the paper has submitted a while ago, but have you tried like a new reasoning model lately? Because I found that for previous models like GPT-4, they just like when you ask questions about ask them to understanding the code, they would just like say something that sounds intelligent, but just like basically nonsense. But recently, when I play with like O1 and O3, it sounds like they can understand like the code a bit better. So have you tried them with like O3 and see if it's like able to detect the vulnerability better?
Yes, this is our ongoing project with testing that reasoning models, specifically that O1 and O1 mini and O3. Basically, we are also testing that DeepSeek R1 as our experiment, part of our experiment. We are still seeing the progress is going, but unfortunately, right now I do not have any results. But I do understand that a reasoning model can be performing better than the traditional models.
Okay, thank you.
Okay, well, they are thinking. I have one question. I'm wondering whether there's any data leakage problem in your evaluation. So these models are trained. Do you look at like the data set, the time when they trained, and whether your vulnerability data sets are included in their evaluation, their training or not?
So that is a very good question. So about the data leakage, even though we say that open source models is open source, but we still don't know what kind of data is used for training. So for this part, we cannot prevent any data leakage. But in our experiment, we actually prevent data leakage. We actually, for each prompting running, we just fully offload the model and reload the model into the memory to prevent that previous system prompt can occur some errors in the next prompt. So that is one prompt strategy where that data leakage strategy we're using for preventing that. And also, we also mentioned about our few-shot learning. For the few-shot learning, we actually exclude whatever including the system prompt in the data set for the experiment. So that is, I think, is more better for the data leakage, at least for this context.
Speaking of the few-shot learning, can you give some more details, like what for each, let's say, vulnerability? What kind of few-shot examples you provide? Because your conclusion is like it's actually making it worse. So yeah.
Yes. So for this one, we're actually using randomly selected to one vulnerable code from our data set and a non-vulnerable code from our data set, and giving input that entire source code into the prompt, and it's stating that this code is vulnerable or not vulnerable, and into the sys prompt, and then ask the model to analyze whatever is going to be input for the next round. So that is what we have doing in the few-shot learning, a few-shot experiment.
So that means you are not actually doing something like retrieving something similar, code with similar vulnerabilities or similar code patterns as example.
Exactly. We are not doing that.
Okay. All right.
This is a very naive way for the few-shot learning, but I would still think it's a very good, promising road for the future development of large language models and vulnerability detection tools.
All right. If there's no more questions, let's thank the speaker again.
Thank you so much.